All right, in this video, we'll continue our discussion of section 3.1. We are continuing with applications using our growth and decay model. We are now going to apply it in physics, to physics, with something called half-life. Half-life is a measure of a stability, is the stability of a radioactive substance. I'm just reading there. Half-life of simply the time it takes for one half of the atoms of initial amount A naught to disintegrate or to transmute into atoms of another element. So we have this measurement um, that we have found that we can measure through substances that might decay over time. This is used in on the next slide where we'll use carbon dating. But a couple examples here they gave us. Radium is like it will go halfway, it'll disintegrate. And I think I don't know if it'll go into something else or not. I am not a chemist, but about 1700 years, you'll have half of that substance left, that element. And then we have other yeah, here it is. Okay, so radium is actually transmuted into radon. Above my pay grade, I like math, but we have this mathematical model that can be used. Okay, so we use a radium isotope, which has a huge half-life, right? Um, so we'll use this in this problem. In the next slide, we'll talk about some carbon dating. Okay, so in this problem, initially 100 milligrams of radioactive substance was present. Okay, after 6 hours, the mass has decreased by 3%. If the rate of decay is proportional to the amount of substance present at time t, find the amount remaining after 24 hours. Also find the half-life. Okay, so they gave us this. This is the indicator to tell us what to do. That tells me that the rate of decay, and we're going to use A for an amount. I think they did above some, yeah, right here. So we'll say A of t, or we don't have that yet, dA dt is equal to some k times a. That's exactly what that phrase says. Now, like I said, you guys don't have to rework this every time. On a test, I would like to see it. So if you need that practice, please do. But this is going to end up as a of t equals a naught e kt. We know our initial amount is that number in front based on our previous problem. So we'll say this as well, a of 0 equals a naught. That's our initial population of the element, the amount of the element, however you want to say it. All right. They also gave us a few things here that we're going to use. I have a of 6 that I have, if we have a number amount, did they give us 100 milligrams? Okay, so we actually can go ahead and replace this a naught. They told us initially is 100. So the initial amount is 100, and then it says after 6 hours there was only decreased by 3%, so this is nice, they gave us 100, so that's 97. And then they want to know after 24 hours what will be there, and then they also want to know what is the half-life. So when will we get 50? Let me write it like that. What is t? All right, so we need to figure out those two questions. So I have my initial conditions. I'm going to go ahead, since I know that the amount is up front, I'm going to just go ahead and put the 100 there. All right, so now my equation is almost where I can plug things in. The problem is I got to figure out that rate, that K. So I'm going to use the data given that I have 97 after 6 hours. So I get 6K. Now notice when I plug it in, the only variable I have is the K. So I'm going to divide by 100. And I get e to the 6K. Okay, this requires us to use an ln. So I got ln of 0.97 equals 6K, because the ln gets rid of the e there. And I have that K is equal to 1/6 times ln of 0.97. You can get a decimal, but I like to keep it exact as long as I can. So a of t then is equal to 100 e to the 1/6 ln of 0.97 t. So there's our actual equation. They want to know what is it going to be 24. So we'll do a of 24, and then I'm going to use my calculator for this. All right, so we're going to get 100, oops, 100 E to the 1 divided by 6 times ln of 0.97 close, close, and then we're going to put in a 24 times 24 to say 24 hours, not years. Okay, 24 hours. After 24 hours, I got 88.529281. And I don't know how they measured it, milligrams of the element left after 24 hours. Now they want to know, when am I going to have half of it left? Well, if I started with a 100, then I'm going to plug a 50 in here. And then we're going to work backwards to find T. All right, let me highlight this so we don't lose it. Okay, that was the 24 hours later. Now I'm solving for half-life. All right, so I get 0.5 if I divide by 100, e to the 1/6 ln of 0.97. All right, and then this is just an ln problem. And don't forget your t, I dropped mine. All right, and I'm just dividing by that. So t is ln of 0.5 divided by, okay, I'm going to put all this in parentheses, 1 divided by 6 ln of 0.97. Close, close. I think that works. Right. So ln, I'm just double checking my type. Yeah, it looks correct. So this says after 136.5394 hours, half of that element would be left. All right. So the method isn't changing a whole lot. It's a lot of just plug in T and an output to find K. Once you do that, then you plug in your T to find your new output, or they give you an output like we just did, a 50, half of it, right? If they do that, then you can still, you just solve backwards. Again, if you take a look at all this work here, it is all algebra. The only calculus here involved was something we assumed. Right there, that's it. All right, so we have one more model here in this video that we're going to take a look at, and then we'll switch applications. All right, so I hope this is making sense. I feel like it's pretty straightforward. It's just a little weird maybe at the beginning. All right, so this next paragraph, I'm not going to read it to you because it's boring. You can read it, it's in your notes. But pretty much what we found, this person, last name is Libby, calculated that half-life of carbon. Carbon 14 is, he said at that time was about 500, 5,600. But in modern years, we have found that the half-life of carbon is actually 5,730. That's what we're using now. So what this does is the ratio of C14 to the stable C12 in the atmosphere appears to be constant, and as a consequence, proportional amount of the isotope present in all living organisms is the same as in the atmosphere. This is the big deal here. This is why we can find this this amount we can tell. Okay, so we're going to look at an application. This is done exactly with the same formula. I'll show you. We're going to set it up. Usually when I have students and I give problems like this, that it's like a wall of text, it's less, it happens less at this level. But I have students that look at these giant paragraphs and they're like, nope, and they move on. As a math person, when I see giant paragraphs like this, I'm like, oh, great, cool. I have a lot to work with. When I have a problem that like literally the problem is 7 words, I'm like, oh gosh, I hope I have stuff to mess around with. So please don't be intimidated when you see these. Just know that you're about to give a lot of information. Okay, so this is a problem out of the book that I liked. The Shroud of Turin, which shows the negative image of a body of a man who appears to have been crucified, is believed to have many, is believed by many to be the burial shroud of Jesus of Nazareth. In 1988, my birth year, the Vatican granted permission to have the shroud carbon dated. 3 independent scientific laboratories analyzed the cloth and concluded that the shroud was approximately 660 years old, an age consistent with its historical appearance. Okay, using this age, determine what percentage of the original amount of C14 remained in the cloth as of 1988. All right, so this uses that exact same model. It's that growth model. So dA of dt, the amount left, is directly proportionate to the amount that is there. All right, so we don't have to use diffeq to get to that. We already did. We know that the amount of t, or amount with respect to t, is going to be the initial amount, e to the kt. All right, we have a couple. I'm going to go ahead and say A of 0 is A naught, so we have that. And then what they're wanting is they're wanting to know how much of the element is left at 660 years later. So we know we can use this because we know the half-life of carbon. So the half-life of the original amount of carbon contained will be the initial amount times, and then we know what the time is. It's 5,730. That's what they told us up there. Times, and then not T, but K. That was the T. After that many years, I'm guaranteed the amount of carbon in anything on our planet will be half there. That's a strong statement. I'm going to retract it. As we know in these examples, I'm not a chemist, so I don't know where that breaks. I'm scared to say that. So anyways, this is our carbon stuff there. I can divide both sides by A naught, and this will lead us straight to K. So any half-life problem will be set up that same way. All right, so now this is just an ln problem. I'm going to change it to 0.5 just for my calculator. And then I know this is equal to 5730K. I have it as a decimal here, so I'm going to go ahead and just give it to you guys instead of pulling my calculator up. I got K is negative 0 point. Actually, let's use the exact. Let's do that. I didn't do that in my notes, but let's do it here. I know it's just ln of 0.5 over 5730. This is what I'm just going to put in my equation. So this tells me A of t is equal to whatever the original population is. Right, and then I got E to the ln 0.5 over 5730 t. And they just want to know how much of the element is going to be left after 660 years. So you might be like, oh, well, how do I figure that out with the A naught? Well, remember, A naught is the original amount. So when I multiply this out, this is what I'm going to get: 0.9232650,334. That's just the E number. We're plugging 660 in times A naught. So this is a number times the amount that we started with. If that number was 0.5, that'd be half. So 0.92 is just roughly 92%. So 660 years later, there was 92% of the cloth left. So that is the problem there. It's again just algebra worked backwards, but really like the trick is understanding what does this mean? Maybe that trip you up. But I like these. These are pretty straightforward, simple applications that work off this very simple idea of a rate, the directly proportional. All right, the rest of the section, we're going to look at a few more applications, and then we're going to move on to higher order diffie qs.